Yes, it's taking some time.
Yes, okay. Good afternoon, everyone. It is a pleasure to have you here with us, Olivier Gaudoin. Olivier received the Master and PhD degree in Applied Mathematics from Grenoble University, France. He is a professor at University Grenoble, Alpes, France, in the Graduate School of Computer Science and Applied Mathematics, Director of International Relations of this school. His research interests are probabilistic modeling and the statistical analysis for reliability of complex systems, including aid and maintenance modeling, competitive risk, goodness of the test, and random process in reality. Olivier is a good relation in Heparin system. Is a have a lot of publication about this issue. Olivier, it's a pleasure to hear this with you. Feel free now.
Okay, so thank you for the presentation, and I would like to start by thanking very much Vera for giving me the opportunity to participate to this seminar, and also to meet again my good colleagues from Brazil, Gustavo and Enrico, who visited our team in Grenoble some time ago. So I hope that it will be possible soon to travel again and be able to see you face to face again. So, well, where is my presentation? I'm not used at all to I never use Google Meet, so I'm not sure that it's okay. Do you see my presentation?
It's okay. It's okay. Appear good for us.
Yes, but I cannot change the slides. Oh, I'm sorry, there is a problem. I do it again.
Oh, Maria Luísa, você está aí. Só um oi para você.
Okay, is it okay now?
Yes.
Yes? Okay, thank you very much. So the work I will present today is a joint work with a team of colleagues from the City University of Hong Kong, Shaolin Wang and Min Xie, and also Laurent Doyen, some of you know him very well, and Christophe Béranguet, who are from Grenoble. So the work will be published in a paper to appear in Applied Stochastic Models in Business and Industry very soon. So the outline of my presentation, I will first introduce the problem by a motivating example from real life. I present a very quick literature review, the model formulation. You will see that we have two models in the presentation, and I will end by a few words of conclusion. So the problem we have comes from a collaboration we have with EDF. EDF is the French electricity company. So we are used to work with them because they have very interesting reliability and maintenance problems. They have real data, and it's very exciting for us to discuss with the engineers and provide solutions to real problems using probability and statistics. So the problem we are concerned with today is about the steam generators of nuclear power plants. So you can see here a steam generator. So in the generator, the water circulates. You have hot water here and cold water there. And what you can see here is the high number of tubes. There are tubes in this steam generator, and these tubes are subject to degradation. The degradation is a clogging. It means that some deposits accumulate on the tubes, and more precisely on the support plates of the tubes. And when the clogging is too high, the generator cannot work correctly. And it can lead possibly to a failure. But the main problem is that we have a degradation of the performance of the generator. So it's important to be able to control the degradation of the steam generator, but it's very difficult to analyze the degradation because it's difficult to see the degradation is inside the generator. And so it's difficult to have a fair, a clear measure of the degradation. That's why the engineers have several ways to analyze the degradation of the generators, and they have 3 different ways of measuring the degradation. So we have 3 degradation indicators. The process is confidential, so I cannot explain to you how the indicators are computed. But anyway, it means that we have 3 sequences of indicators, which are 3 different measures of the degradation of the tubes in the steam generator. And moreover, we also have maintenance actions because, of course, the engineers want to prevent the clogging and to remove the clogging. So sometimes when the tubes are plugged, they are replaced by new ones. But more often, we have chemical cleaning. And the effect of chemical cleaning is to reduce the clogging. So it's an improvement, a reduction of the degradation. From that, it's possible to have data. So here I have given an example of the measurement of the 3 indicators on the steam generator. And what can be seen here is that we have several features which are involved in the phenomenon. And the first one is a question of dependency. First of all, when you have successive measure of the same quantity, of course, you have a trend in the degradation. So here you see an increasing of the red points. So it means that the degradation is increasing. We have points and crosses, and in fact, points and crosses are 2 different measures of the same indicator. Of course, they are very correlated, very dependent. So we have a dependency about the trend of one indicator. We have a dependency between 2 measures of the same indicator. And we, of course, have a dependency between the different indicators of the degradation. So it's obvious here that you have a dependency between indicator 1 and indicator 2. It's less obvious, of course, for indicator 3. But in fact, the 3 indicators are linked to the same phenomenon of degradation. So they are indeed dependent. You can see here in blue the time of a maintenance action. So here, this maintenance action is a cleaning, a chemical cleaning. And when you see the difference of the measure of the degradation before maintenance and after maintenance, it is clear that the maintenance has a positive effect. The maintenance has reduced the degradation, but the maintenance has not reduced the degradation to 0. We have here a degradation which is weak, but not equal to 0. And we also have a problem with that about heterogeneity, because these generators are subjected to environmental conditions which vary with time. And for instance, we have a chemical environment which is constant for a certain time and which changes. So this can be in a model taken into account as covariates, observed covariates. But we may also have unobserved heterogeneity, and sometimes there can be random effects on the degradation. And finally, as regards the data, we have missing or partial information. One problem we have, which is in fact very important in practice, is that the indicators are not always simultaneously recorded. For instance, if you see indicator 1 and indicator 2, you can see that it seems that in most cases, the indicator 1 and indicator 2 are simultaneously recorded at the same time. But if there is here a problem, for indicator 1, the indicator 1 is measured before maintenance here, because you see that the value is on the upside of the plot. And here, for the indicator 2, the indicator is measured only after the maintenance. So it's not the same time, and it's more clear on the situation, because on the indicator 3, it's clear that indicator 3 is not measured at the same time at the other indicators. And we also have a problem of censoring, because we have no observation of indicator 3 before maintenance. And of course, we don't know what is the effect of the maintenance, and there are also unobserved heterogeneity. So in our problems, we have data with all these features. And so what we want to do is to propose a degradation model which take into account all these features. So the first feature is that we have several dependent indicators or dependent measures of the same indicator. So it means that we want to take into account multivariate degradation processes. The second feature is that we have covariates. So we want to take into account the heterogeneity in the operating conditions. So I talk about chemical conditioning, but it's also the case of temperature. And in our situations, these conditions vary over time. So the covariates are time variant. And finally, I have said that we have maintenance, but the maintenance do not renew the system. The system after maintenance is, in fact, in an intermediate state between the minimal repair and perfect repair, or as bad as old situation and as good as new situation. So in fact, there is a huge literature about degradation modeling, and many papers are dealing with one aspect or two aspects about these three. For instance, there exists some papers about covariates in bivariate degradation processes, but to our knowledge, there is no paper exists which try to take into account all these features at the same time. So our aim was to build such models. And in fact, we proposed two ways of modeling this situation. One way is based on the degradation path, and another way is based on the time scale adjustment. But the two classes of models are made to take into account these three features. So what I will present to you today is the ideas on these models. But of course, in our problem, we have real data, and we have in mind the fact that we will have to analyze this data, and so statistical issues about the data and the model have to be treated afterwards. So a very quick literature review on the three aspects of the problem. As regards the multivariate aspect, so the dependency between the degradation processes, there are a lot of papers which take into account the dependency by using copulas. We have also another kind of papers which use multivariate classical models. The Wiener process is very well known, and the gamma process or inverse Gaussian process. So we have papers dealing with bivariate Wiener processes, for instance. We have a few papers about a trivariate reduction method, and this method aims to build a multivariate degradation process based on univariate degradation processes by a reduction method. But we have only a few work with the dimension is greater than 2. In my example, I have presented 3 indicators, so we have a dimension 3, and so we need to take into account a dimension which is greater than 2. So only a few papers deal with this issue, and they are very recent, as you can see. So among all this literature, our choice first is to take Wiener processes, because in our situation, the degradation is not strictly monotone. Is the degradation where monotone? We can think of using gamma processes, for instance. It's usual in this field. But here, since we don't have this monotonicity property, we have chosen to use Wiener processes. And the other choice we made is that since we have several indicators of the same degradation phenomenon, we adopt an idea presented by these authors here in a paper. And the idea, I will present the idea in details after, is to build a multivariate Wiener process from several univariate processes sharing the same noise. Now, a quick literature review about maintenance effect in degradation models. Well, most of the paper assume that the effect of maintenance, that the maintenance is perfect. So the effect of maintenance is to replace the system or to leave it as good as new. And in this kind of papers, the aim of the papers in general to optimize the maintenance policy or the inspection policy. But here, in our case, maintenance is imperfect. So there are only a few papers dealing with imperfect maintenance in degradation, because we have a lot of papers dealing with imperfect maintenance in lifetime models. But in degradation model, it's more recent. And so we will use their ideas here. And the idea of this paper is to say that an imperfect maintenance reduces something, but it can reduce the degradation level, but it can also reduce the age of the system, because most of the work about imperfect maintenance for lifetime models deal with the concept of the reduction of virtual age. So the idea is to mimic this idea of virtual age, but for degradation processes. So we have these two approaches, and we have chosen to tackle both approaches. We have chosen one approach in which the maintenance has an effect on the degradation level itself, and another model in which the maintenance will reduce the virtual age. And finally, about heterogeneity, we have only a few work in this area. First of all, when we consider dynamic observed covariates, the main way of modeling this situation is to use degradation model in which some parameters are functions of the covariates. But we have been also interested in step trace accelerated degradation test, because, as you will see later, our covariates are piecewise constant. And this very specific case is close. It's not similar, but it has something close to the step trace accelerated degradation test. And finally, Vera told me that recently, Vera and co-authors have published a paper in which the heterogeneity is taken into account with frailties. So in our case, we will take into account only the observed heterogeneity, and we will use piecewise constant covariates. So that's all for the literature review. Now I present the model formulation. And in fact, if in our modeling approach, we will present several models which have common features and also specific features. The common features are that the covariates are piecewise constant, and the degradation process is multivariate Wiener. And the specific features lies on the influence of covariates and maintenance. In the first model, which we call this model degradation path adjustment model, we assume that the effect of covariates and maintenance is directly on the degradation level, or the degradation path or degradation rates. I will explain that very quickly later. And in the second class of model, we assume that the effect of covariates and maintenances is to modify the virtual age or the time scales governing the degradation process. So let me start by an explanation regarding the covariates. we have several covariates. So let's say that we have m covariates, and they are piecewise constant. So piecewise constants mean that there are constants in an interval, and there is a time at which the covariants change their values. So we will denote tau j all the time points at which at least one of the covariates change its values, because of course we have several covariates, but they don't change their values at the same time. The value of the covariate number m during the time interval number j will be denoted smj. And therefore, the information about all the covariates on the interval tau j minus 1 tau j is given that by this vector here, sj, which gives the value of the m covariates on this time interval. And finally, the piecewise constant covariates process is given that by this expression here. And so in each time interval, we give the value of all the covariates. In our example, we have something similar to that. So these are not real data, but they are similar to real data. In our example, we have a covariate which is fully constant. So it's the case here. But we also have a covariate which is piecewise constant, so changes its values at some points in time. So here we have given an example in which the change of the covariate is periodic. It's not the case in practice, but it's easier to present this situation. Now, the multivariate degradation process. So we will assume that we have n components of the degradation process. So in our situation, we have n equal to 3 degradation indicators. So for each of the components of the degradation, we have a degradation process. So xi of t will denote the baseline degradation process of component I. By baseline, I mean that it's under some level of the covariates, which is considered as the nominal level, S0. Now we want to express the dependency between the degradation indicators. And that's why we used the approach of Hong, Ye, Ling, because we think that their assumption reflects what we have in our example. So in our example, we have several indicators of the same degradation process. So we can think that basically we have the same degradation process, and we have specificities of each indicator. So that's why we can use the idea of Hong, Ye, and Ling, because they think that in their model, we have a common noise process, which models the dependency among all the degradation processes. And we also have individual noise processes, which describe the specificity of each degradation process. And they've assumed that the noise processes are Brownian motions, so it's good for us because we want to use Wiener processes. So it means that the baseline degradation process of the component I of the degradation can be described this way. So you can see that we have first a constant, I mean not random term, mu I lambda of t. So mu I are drift parameters. They are linked with the rate of degradation. And lambda is a monotone function, which is increasing because we think that basically the degradation is increasing. And the idea is that the degradation can be linear, but not linear also. So if lambda of t is equal to t, the degradation will be linear. It is the usual case. But by taking into account any function lambda of t, we can take into account nonlinear degradation trends. And for instance, we will use here power functions for this function lambda of t. Here you have the common noise process. So this term is the same for all xi, for each I. So it means that our degradation processes share the same basic process. So this represents the basic degradation phenomenon we want to measure. And here we have the second part, which is another Brownian motion, which is dependent of I. So it means that this part is specific to the component I of the degradation. The parameters zeta 0 and zeta I are diffusion parameters, and the BI's are independent standard Brownian motions. So if we make a very simple analysis of this model, of course, the expectation of the degradation is mu I lambda of t. So this term will represent the mean degradation. The variance of the xi of t has this expression. So we have two components. One component comes from the common process, and one component is specific to each degradation process. When you compute the covariance between two different components of the degradation process, that's what we obtain here. And when we compute the coefficient of correlation, this is the value that we have. And the interesting thing is that this value is independent of t. So in this model, the correlation is the same for all the time of the observation. We don't know if it's a reasonable assumption in practice. So this kind of thing has to be checked on the data. But it provides a model which is quite simple. And then you can see that when zeta 0 is equal to 0, the components are not correlated, and so they are independent because we have Wiener processes. And when zeta 0 tends to 1, you have here a strong dependency. Sorry, not if zeta 0 tends to 1, if the xi tends to 0. So finally, it's also possible to develop a matrix writing of the model, which is very simple. And the x of t is a Gaussian vector, so it's quite easy to manipulate this model. But this model without covariates. This is an example of the simulation of the multivariate degradation model. So we have three components in our situation: the black, the red, and the blue. I have chosen three values of the parameter mu I, and the highest mu I is, the higher the degradation here. So you see that we have a high trend here and a weaker trend here. We have chosen here a lambda of t, which is not linear, but very close to linearity. And there are two values of zeta 0. So we have zeta 0, I remind, represents the correlation. And then we have a weak correlation here and a strong correlation here. And you can see the strong correlation here because, for instance, here, you see that the shape of the degradation process for the blue, the red, and the black one, their shapes are very close because we have a strong correlation. Here, it's less easy to see something. Now, I will present our two models. So let me recall that in the first model, the impact of the covariates and maintenances is on the degradation, and on the second model, it will be on the time. So for our first model, degradation path model, the covariates and maintenance influence directly the rates and paths of the individual degradation processes. So let me explain that. First of all, we'll say that the covariates have an influence on the degradation process, and we will denote that by saying that xi of t and sj is the degradation process of the component I of the degradation in the jth interval. So it means that when the values of the covariates are sj. If we make the assumption that the covariates impact only the drift parameter, the drift parameter is the mu in the precedent model. So this mu here will now be dependent on the covariates. So the notation is moved to mu I of Sj and gamma I. So Sj is the value of the covariate, and gamma I are the parameters which express the effect of the covariate on the drift parameters. So of course, any kind of expression can be chosen for mu. We have chosen an exponential expression. So this is very usual in, for instance, in Cox models or proportional hazard models or in accelerated failure term models. So here we have a parameter, gamma I, which is made of individual parameters here. Gamma I m expresses the effect of the covariates number m on the component I of the degradation. Now let us denote xi of t st, the degradation process of component I, subject to all the covariate process st. The assumption we make is that the rate of degradation depends only on the current covariates, but not on all the history of the process. It could be possible to build a model in which the drift parameter may depend on all the covariates that occurred before, but the model would be very complex. And so we have chosen this very simple assumption. And therefore, it's possible to show that the degradation process has this expression. In fact, here, even if the rate of degradation in an interval depends only on the current covariates, when you are computing the degradation process, it's necessary to take into account all the previous covariates. That's why we have this expression here for the drift. But the variance components have the same expressions as before. This is an example of the path of the model in which we take into account covariates. So here, I have used the two covariates presented in a previous slide, and the free component of the degradation presented also in the previous slide. Now, what is added is an assumption on the effect of the covariates on the degradation using the model I proposed. And we have these values of the parameters gammas. So what can be seen here is that, well, I have chosen only positive parameter except one here. Gamma 3,2 is negative. It means that the covariate number 2 have a negative effect on the component number 3 of the degradation. By negative effect, in fact, well, when the parameter is negative, in fact, the effect is positive because when gamma is negative, it means that the covariate helps to reduce the degradation. And when the gamma is positive, the covariate increases the degradation. That's why here, by the black curve is the degradation path when you have no covariates, and the red one is when you have covariates. So you can see here that for the first two components, the covariates have an effect on the degradation process. They have increased the degradation process, but here, because of this gamma, which is negative, the covariate have reduced the degradation process. Now let's move to the effect of maintenance. We will assume that imperfect maintenance actions, here I talk only on the preventive maintenance because in our example, the system is never so degraded that a failure happened. So we have considered that we have no failure. But of course, it could be possible to take into account the possibility of having a failure. And it's normal to be interested in the problem of computing, for instance, the remaining useful life or the mean time to failure of the system. But in our data, we have no failure observed. That's why the maintenance actions are only preventive maintenance actions, such as chemical cleaning. They are performed at time tk, and in fact, the time of the maintenance are different from the times where the covariates change their values. So for the covariates, the times were denoted tau j, and for the maintenance, the times are denoted tk. As for the covariates, we assume that the effect of the PM is to modify the level of degradation. So in order to express that, we have chosen to use an ID which is similar to the virtual age model for lifetimes models, because in fact, with Laurent Doyen, we have worked a lot on this kind of models, and I know that Gustavo and over here have also worked on this kind of models, and we have proposed the arithmetic prediction of age models. And then what we wanted here is to use a similar ID in degradation models. So for that, let us denote xik, the intrinsic degradation level of component I just before the maintenance number k. By intrinsic, I mean I consider first a degradation process with no maintenance. And when you have a maintenance, the degradation process is denoted x tilde in order to take into account the difference between the process without maintenance and the process with maintenance. So xi will be the degradation level of the component just after the kth PM action. So what we want to do is to express the difference between what happened before maintenance and what happened after maintenance. So eta ik will denote the degradation level after the PM activity. So it's in fact nothing but xi of tk plus, and we will denote by delta ik the degradation reduction factor. And by the similarity with the lifetime models, we want to have a model in which when delta is equal to 0, the maintenance effect is minimal. When delta equal to 1, the maintenance effect is perfect. And when delta is below 0 and 1, we have an intermediate effect. So it means we have an imperfect maintenance effect. So the idea was proposed, in fact, by Mercier and Castro 2 years ago, and they called the model arithmetic reduction of degradation with memory 1. It is a reference of our arithmetic reduction of age with memory 1 model. And in this model, the idea is that an imperfect maintenance action removes a proportion of the degradation accumulated since the last maintenance. So this can be seen in this formula here. This formula means that the degradation level just after maintenance number k is equal to the degradation level after the previous maintenance, plus this increment of degradation is the increment of degradation of the process without maintenance between the k-1 and the kth maintenance. So it's we arrive at the time tk, and then we remove delta ik multiplied by this increment. And in fact, this is exactly the proportion of the degradation accumulated since the last maintenance. And having set this relation, it's possible to derive the expression of the degradation process after the maintenance. And the expression that is obtained is the following one. When we built lifetime models, we have taken into account the ARA 1 and ARA infinity model. And so Mercier and Castro did the same thing here. They have proposed the arithmetic prediction of degradation with infinite memory model, in which the imperfect maintenance action reduces the degradation of an amount which is proportional not only to the increment of the degradation since the last maintenance, but which is proportional, in fact, to the current degradation level. When the translation of this hypothesis is this formula. well, it's not necessary to explain it. And from this formula, we can derive the value of the degradation process after time tk. It's not very simple, but it's not too complex too. Well, now it's possible, having defined this model, to simulate them and to see how they work. And so here, I have taken a model in which we have both the covariates and the imperfect maintenance actions. So the assumptions about the imperfect PM is that the PM are periodic and the periodicity is 25. We have a delta is the effect of maintenance. By taking delta equal to 0.5 means that we have an efficiency of maintenance which is exactly in the middle between perfect and minimal maintenance. So it's a quite efficient maintenance here. And for simplicity, we have chosen a case where all the deltas are equal. It is not necessarily the case in practice. So here, what you can see is the black or dotted line is the degradation path with covariates only. It's the curve that was presented in the previous slide. And in blue and red, what you have is the same model in which we have added the imperfect maintenance actions. What can be seen here is also, the model ARD1 is in red and the ARD infinity is in blue. So what we can see here is that with the ARD infinity model, the reduction of the degradation is greater than for the ARD1 model. And that's the main thing that we can see. In fact, if you have a closer look at the model, you can see that it's normal that after the first maintenance, the two models are exactly the same. And here, because we have a greater variance in the component 3, you can see that the paths become to be more hectic. Finally, some remarks about this first class of models. Of course, if we consider that the mu I does not depend on the covariates, what we obtain is the model when there are only imperfect maintenance effects. And when you choose delta I k is equal to 0 for all k, it means that the maintenance has no effect, and so we have a model with only time variant covariates. An interesting property, I have no time to show that, but it's written on the paper. In fact, we can prove that in this paper, the correlation structure, when we add maintenance and covariates, is exactly the same as for the initial model without covariates and without maintenance. It's because the effect of maintenance and covariates is only on the drift parameter. There is no effect on the variance part of the model. And so, well, it's easier for the mathematical computation, but is it really realistic to assume that? It's not sure. So we will have to check if this kind of assumption is possible in a practical case. And another thing is that it's easy in this situation to allow another possibility. The possibility is that an imperfect maintenance may increase the degradation rate, because here you can see that there is a kind of parallelism between the case with no maintenance and the case with maintenance. So it's the same train here. But it's possible to consider that we change the train, and for instance, having a thread this way here, because in practice, we have observed that a maintenance can, in fact, reduce immediately the degradation level, but increase the speed of degradation after the maintenance. Then it's possible to take this thing into account in this model. So that's all for the first model. And now let me talk about the second one. So the second one make the assumption that the covariates and maintenance have an effect on the time scales. So it's the equivalent of the virtual age models for lifetime. It's more complex, in fact. So here I want just to give you an idea of what happens in this case. So the equivalent of the notion of virtual age will be called here the equivalent operating time. So we assume that, first we talk about covariates, we assume that for degradation process which is exposed under a certain covariate level for a certain time period, there exists an equivalent operating time for this process over another covariate level. And having made this assumption and using the idea of virtual age models for lifetimes, it means that we introduce a parameter, theta ij, which is the equivalent operating time of the degradation process I under the covariates Sj. And then in the jth period, so xi, I'm sorry, I have a... T'es là? Oh. Okay, we had a problem with the alarm here. Well, let's come back to the model. So we said that we have defined this equivalent operating time, and then the degradation process can be written this way. On the jth period, the degradation here is equal to the equivalent operating time plus the time elapsed during the jth period, and when the covariates applied are the Sj. And here it's maybe more easier to understand. By continuity in tau j minus 1, we can show this, this relation here. So it means that it's an illustration of this notion of equivalent operating time. Exposing the component I under covariates Sj for theta ij time units is this value of the degradation. So it's equivalent to exposing this component under the covariates Sj minus 1, but for a time unit which is defined this way, by this value of theta, and theta j minus 1 minus theta j minus 2. So this is what we mean by the equivalent operating time. We also have to have an assumption on the degradation process, on the way the covariates have an influence on the degradation process. So we have made the assumption that this effect is on the time scale. So it's we make this assumption here, as in the Peng and Seng paper. And the idea is to do something which is close to an accelerated failure time model. It means that the effect of the covariates is to multiply the time by something which is dependent on the value of the covariates. And of course, if the factor here is greater than 1, it means that the effect of the covariates is to increase the degradation. And if the covariates is less than 1, the effect is to reduce the degradation process. And as before, we have chosen an exponential expression, so like in the Cox models, to express this parameter zeta here. And then, then it leads to this expression of the degradation process. And by using this relation here, it's possible to make a relationship between the zeta and the thetas. So with all that, in fact, the model appears to be expressed very simply, because the degradation process under the covariate process has exactly the same expression as the initial process, except that the time t has been transformed and is transformed in omega I of t. The omega I is called the adjusted time scale, and in fact, it has this expression here. So it's quite complex to handle, but what you have to understand is only that we have an effect on the time scale by this way of representing the degradation process. This is an example of simulated data. So in the black, we have the degradation path of our three components of the degradation without covariates. And when we add covariates, we obtain these things here. So as before, I have chosen one negative coefficient here, and the overall are positive. And as before, for the first two components, the covariates have a positive effect. Positive it means that they will increase the degradation. And here, the covariate, only the second covariate, will reduce the degradation. Now we come to the last part of the second model, the effect of maintenance. So here, this will be very similar to what is known for lifetime models. We assume, as before, that we have imperfect maintenance actions at time tk. We denote by wik the equivalent operating time of degradation process I just before the maintenance number k. And vik will be the virtual age of the degradation process I immediately after the kth PM action. So the idea is to express the difference between W and V as before. And so what is the amount of age reduction between these two values of the age? And as before, we use a parameter delta ik, which will express the effect of maintenance such that the maintenance is minimal when delta is 0, the maintenance is perfect when delta equal to 1, and the maintenance is imperfect when you are in between 0 and 1. So the first model is the ARA1 model. So this name is for arithmetic reduction of age. In fact, that's the name that we proposed with Laurent in 2004, based on the previous idea by Kijima. And Mercier and Castro choose to use the same name for the model they proposed on the degradation, degradation process. So we keep this name of ARA1. But the idea of the model is the same, because for the ARA1 model, the effect of the imperfect maintenance is to remove a proportion of the age accumulated since the last maintenance. And this assumption is traduced in mathematical way by this expression. So it's the same as before. The virtual age after maintenance k is the virtual age after maintenance k minus 1, plus the time elapsed since maintenance, the previous maintenance, minus this time multiplied by delta ik. And, the degradation process has the same expression as before, but the W's are not the same, because when in this expression here, the adjusted time scale has this expression, because we have only covariates, no maintenance. And when we add maintenances, we have to take into account the effect of maintenance in the virtual age, and the effect of maintenance is taken into account by this expression here. And we also have an ARA infinity model, in which the assumption is that the imperfect maintenance reduces the virtual age of an amount which is proportional to the complete age, not only the age accumulated before the last maintenance, but the full age from the origin of the system. And then the virtual age has this expression. And when you simulate that, you obtain things like that. And so here you can see that it becomes difficult to identify something, because when in the component 3, we have chosen for the component 3 a strong variance. So with a strong variance, the effect and the effect of the maintenance, which are increasing, because you can see here that we have a small difference between ARA1 and ARA infinity, but here a difference which increases. And then when everything is increasing, at the end, it's difficult to see to give an interpretation of this model, of this path here. Okay, so same remarks as before. It's possible to find the case we have only maintenance, or when we have only covariates as special case of the general model. But there is here another property which is very different as what we have in the degradation path model. In the degradation path model, we had the same covariance structure in the final model as in the initial model. But here, we don't have the same covariance process because of the reduction of age, the maintenance and the covariates impact also the variance of the degradation processes. And the correlation coefficient is no longer independent of t. So it means that this model is more complex than the first one. It may be more difficult to use, but we don't know that yet. Some remarks, some comparison between the models. Well, it's easy to see that when we choose a linear mean path and the mu i's of the first model, which are equal of the mu's of the second model, then the mean of the mean degradation path of the degradation processes are the same for the degradation path model and the time scale model. And when we add PM, we have to add the assumption that we have the same deltas. All the deltas are the same. And in this situation, the two models are also similar. Here we also have a comparison of the proposed model. So in red, you have the ARD1 model, donc a degradation path model. And in blue, the ARA1 model, time scale model. So we have the same parameters, and we change some things. We change the value of beta. You remember that lambda of t is equal to t to the power beta. When beta equal to 1, we have a linear mean path. And here you have a non-linear, but not so far from linear mean path. And we have chosen two different values of delta. 0.25 is a moderate PM efficiency, and 0.75 is a high PM efficiency. So here you have beta equal to 1 and delta equal to 0.25. Here, same delta, but beta equal to 1.2. So what you can see is the effect of having a non-linear mean path. And here you have a linear mean path, but a strong maintenance efficiency. And then it's possible to have a quick view of the effect of all these parameters on the mean path. So basically, what we can see is here, the two trajectories are very close, and here they are very different. And it means that the model are close when the mean baseline path is linear, when the uncertainty level is low, because we are in the component 1 here, and when the maintenance efficiency is small. But if we have a strong variance on the initial degradation path, if we have a strong efficiency of maintenance, if we have a non-linear mean degradation path, then the trajectories of the model are completely different. So I come to the end of the presentation. So in this work, we have built two classes of model. So with the desired feature, we had real data at the beginning, and we wanted to build models which would be able to represent this real data. So we have managed to do that. We have two different models with multivariate degradation, time variant covariates, and imperfect maintenance. But it's only the beginning of the work, in fact, because there are a lot of things to do. The first thing is to use these models in order to compute reliability indicators. So the reliability function, the mean time to failure, the remaining useful life, are we able to compute that with these models? we think that it's possible with the first one, but we are not sure that it's possible with the second one. It's also interesting to study other stochastic properties. For instance, is it possible to derive an asymptotic behavior for these processes? Is it possible to compute higher order moments, or to compare the classes of models more analytically than before? Is it possible to include unobserved heterogeneity, for instance? So there are many issues about the modeling here. And now we come to a very important thing, is the statistical issue, because that's what we want to do with our data. We have proposed parameter. We want to estimate the parameters. We have started to do that. We have some preliminary results about statistical inference. There may be possible identifiability issues, because it may be difficult to make the difference between the effect of a covariate and the effect of a maintenance. Will it be possible to make this difference? We don't know that. Of course, it would be of interest to perform statistical tests, in particular goodness of fit test, in order to do model selection. In our data, we have censoring. We also have indicators which are not measured at the same time. We have also started to tackle this issue. And in fact, it's not easy. We also have preliminary results. It's quite easy when we assume that all the indicators are measured at the same time, because we use in fact independent increments. But when the indicators are not measured at the same time, the likelihoods are much more. It's much more difficult to write the likelihoods. And finally, what we want to do at the end is maintenance planning, because what the guys from EDF want is to, of course, they want to assess the reliability of their system. They want to know if their maintenance are efficient, but the maintenance are costly. So it's important to be able to develop an optimal maintenance plan, also an inspection plan. When should we inspect the system? When should we measure the indicators? When should we do the maintenance actions? Are we able to choose the degree of the maintenance action? And all these things have different costs. We have the cost of inspection, the cost of maintenances, the cost of failures. And so it's an interesting issue to take this into account in order to develop an optimal maintenance strategy for this kind of system. Okay, so that's all. I've come to the end of the presentation. I thank you very much for your attention, and I'm ready to try to answer your question.